In the early 20th century, Albert Einstein revolutionized our understanding of the universe with his groundbreaking theory of relativity. His famous equation E equals mc squared unveiled a profound connection between energy and mass, linked by the speed of light squared. This equation suggested that mass is just a concentrated form of energy, a concept that challenged conventional wisdom. Einstein's equation raised a fundamental question. Why do particles have mass in the first place? What gives them their inertia, their resistance to changes in motion? This question, seemingly simple, has puzzled physicists for decades. It became a cornerstone in the quest to understand the fundamental building blocks of the universe. The answer, as it turned out, lay not in the stars or galaxies, but in the very fabric of space and time itself. It required a radical shift in perspective, a journey into the strange and wonderful world of quantum mechanics. There, amidst the uncertainty and probabilistic nature of the subatomic realm, the answer awaited discovery. The exploration of this mystery, the pursuit of the origin of mass, would lead physicists down a winding path, culminating in one of the most significant scientific discoveries of the 21st century. This is the story of the Higgs boson, the God particle, and its role in unraveling the cosmic puzzle of mass. By the mid-20th century, physicists had developed a remarkably successful framework for understanding the fundamental particles and forces that govern our universe, the Standard Model. This model elegantly described the electromagnetic weak and strong forces, and it categorized all known fundamental particles into neat families. However, there was a glaring omission. While the Standard Model could account for many observed phenomena, it failed to explain how particles acquired their mass. Without mass, particles would zip around at the speed of light, unable to form atoms, stars, or galaxies. The universe, as we know it, would be impossible. This missing piece of the puzzle posed a significant challenge. It suggested that the Standard Model, for all its triumphs, was incomplete. There had to be something more, a missing ingredient that could explain the origin of mass. The search for this missing ingredient became a driving force in particle physics. It led to the development of new theories, new experiments, and ultimately to the construction of the most powerful particle accelerator ever built, the Large Hadron Collider. In the 1960s, a young physicist named Peter Higgs, working independently at the University of Edinburgh, proposed a radical solution. He suggested that space is permeated by an invisible field, now known as the Higgs field. This field, he argued, interacts with particles, imparting mass to them. Higgs' theory was as elegant as it was revolutionary. It proposed that particles acquire mass through their interaction with this pervasive field, much like objects acquire weight by interacting with the gravitational field. The stronger a particle's interaction with the Higgs field, the greater its mass. This idea was initially met with skepticism. The concept of an invisible field permeating all of space was difficult to grasp, and there was no experimental evidence to support it. However, Higgs's theory provided a compelling explanation for a fundamental mystery, and it soon gained traction among physicists. The hunt for the Higgs boson, the particle associated with the Higgs field, had begun. Finding this elusive particle would provide the crucial experimental evidence needed to validate Higgs's theory and revolutionize our understanding of the universe. Visualizing the Higgs field and its role in imparting mass can be challenging. One common analogy is to imagine a crowded room representing the Higgs field. As a celebrity tries to move through the room, they attract a large crowd, making it harder for them to move. This crowd represents the Higgs field interacting with the celebrity, giving them mass. Another helpful visualization is the Mexican hat potential. Imagine a sombrero resting on a table. A marble placed on the hat's crown represents a universe with no mass. This state, however, is unstable. The marble will inevitably roll down to the brim, breaking the symmetry. This rolling down represents the Higgs field acquiring a non-zero value, giving particles mass. This analogy helps illustrate the concept of spontaneous symmetry breaking, a crucial aspect of the Higgs mechanism. In the early universe, the Higgs field had no preferred direction, much like the marble at the hat's crown. As the universe cooled, the Higgs field settled into a specific state, breaking the symmetry and giving particles mass. Understanding these concepts is crucial for grasping the profound implications of the Higgs field. It's not just an abstract mathematical construct, but a fundamental aspect of our reality, responsible for the very existence of the universe as we know it. Section 5. The Colossus of Modern Science, the Large Hadron Collider. To find the Higgs boson, physicists needed a tool of unprecedented power and precision, the Large Hadron Collider, or LHC. Located beneath the French-Swiss border, the LHC is the world's largest and most powerful particle accelerator, a marvel of modern engineering. Inside the LHC's 27-kilometer ring, protons are accelerated to nearly the speed of light and smashed together in colossal collisions, recreating the conditions that existed fractions of a second after the Big Bang. These collisions generate a shower of particles which are then analyzed by massive detectors. The LHC is a testament to human ingenuity and international collaboration. Thousands of scientists and engineers from around the world contributed to its design, construction, and operation. The data it produces are analyzed by a global network of researchers, highlighting the collaborative spirit of modern science. The LHC's immense energy and sophisticated detectors provide the best chance of creating and detecting the elusive Higgs boson. The search for the Higgs became synonymous with the LHC, capturing the imagination of the public and igniting a new wave of interest in particle physics. Section 6. Elation and Validation, the 2012 discovery. After years of anticipation, on July 4, 2012, scientists at CERN, the European Organization for Nuclear Research, announced the discovery of a new particle consistent with the properties of the Higgs boson. The announcement sent shockwaves through the scientific community and beyond. The discovery was a triumph of human endeavor, a testament to the power of scientific inquiry. It was the culmination of decades of theoretical work, experimental ingenuity, and international collaboration. The elusive Higgs boson, once a theoretical construct, had been brought to life in the heart of the LHC. The emotional impact of the discovery was profound. Peter Higgs himself, along with his colleague François Englert, was present at the announcement, visibly moved by the moment. The discovery validated their theoretical work, confirming the existence of the Higgs field and revolutionizing our understanding of the universe. The discovery of the Higgs boson was not just a scientific breakthrough, but a cultural moment. It captured the public imagination, inspiring a new generation of scientists and reminding us of the awe and wonder that scientific exploration can evoke. Section 7. A triumph for the Standard Model and beyond. The discovery of the Higgs boson was a major triumph for the Standard Model of particle physics. It filled a crucial gap in our understanding of how particles acquire mass, providing a complete and consistent picture of the fundamental building blocks of matter. The Higgs boson's discovery validated the Standard Model's predictions, solidifying its status as one of the most successful scientific theories ever devised. It demonstrated the power of theoretical physics to make accurate predictions about the universe, even at the most fundamental levels. However, the discovery also raised new questions and pointed towards physics beyond the Standard Model. While the Higgs mechanism explained the origin of mass for fundamental particles, it did not address the mystery of dark matter and dark energy, which constitute the vast majority of the universe's mass-energy content. The Higgs boson's properties, such as its mass and interactions with other particles, provided clues about the nature of physics beyond the Standard Model. These clues are being actively pursued by physicists who are eager to unravel the deeper mysteries of the universe. Section 8. The Uncharted Territories of Physics. What mysteries remain? The discovery of the Higgs boson marked a significant milestone in our quest to understand the universe, but it also highlighted the vast uncharted territories that remain to be explored in physics. While the Standard Model, now complete with the Higgs boson, provides an elegant framework for understanding the fundamental particles and forces, it leaves several profound questions unanswered. These questions include the nature of dark matter and dark energy, the origin of neutrino masses, and the unification of all fundamental forces, including gravity. The search for answers to these questions continues, fueled by the curiosity and ingenuity of physicists around the world. The LHC, along with other experiments, will continue to probe the frontiers of our understanding, searching for new particles, new forces, and new principles that govern the universe. The discovery of the Higgs boson was not the end of the story, but rather the beginning of a new chapter in our exploration of the cosmos. As we delve deeper into the mysteries of the universe, we can be sure that many more surprises and wonders await us, pushing the boundaries of human knowledge and inspiring future generations of scientists.